This is your previous assignment. Please feel free to take your paper now before we start. The TA is going to arrange for a review session in case you have any question, any complaint. Hi. Yes. It's supposed to be 10 days from the release date. I don't know which one. It will be 10 days. I think the TA released it. Then the setting was hidden from student and nobody could access it. So I asked him to extend it, to keep it 10 days from whatever he make it public. But I will ask him to make it clear. All right. Feel free to take your paper for the previous assignment. As we discussed last time, we're going to have the second assignment today at the end of the class, okay? You probably could find it somewhere. So it's not there at all. The good thing, he took picture of every paper. So find it. Okay. Yeah, no worries. We took picture of all papers. So in case if we miss something, you'll probably have it. Hi, good morning, Elvis. I got your email last time. Yes. Everything good? Okay. Hi, good morning.
Did I use the homework? Was it
This one?
so we have one?
This is the in-class assignment. We are going to have the second one by the end of this lecture.
Okay.
Yeah, based on your colleague request, they asked to have the assignment at the end of the class, not at the beginning of the class. Because if someone came late, then they still have the opportunity to have it. As we said, we are going to have a review session for 2 hours. Some days, either Friday or Monday, I will ask the TA to agree to discuss it with you, agree on time, and so on. Okay, we'll have it over Zoom, so you won't find it difficult to attend it. But for those who wonder about the answers, we already discussed them when we met online. I think for lecture 6 or 7, right? We already went through the solution. We discussed ways to solve the questions and all this stuff. All right. So good morning. Today we'll continue with optimizing Boolean algebra equation for presenting digital design circuits. And this is an extremely important topic because this is actually how you're going to represent the circuit, but not using logic gates and all this stuff, okay? So your circuit could have like thousands of gates, but at the end of the day, you could represent the functionality of it using very simple equation that you can share with your peers, with your friends, with your colleague, with your classmates, and so on. So we stopped last time at the several important theorems. And those theorems, some of them make sense, so you don't need to remember them. Some of them really, you have to remember them. You could extract them. You could coming up with all those equations, but it will take you some time to prove them and verify them and all that. So my recommendation, at least the last 4 theorems, you need really to remember them, okay? If you want to make really quick in solving those questions. The rest, I think it's really trivial. It's very similar to algebra equation. Whoever like trying to simplify mathematical equation with 3 variables, 2 variables, the exact same story. Okay. Today, we are celebrating the first day of Ramadan, which is fasting for Muslims. And it's amazing that fasting is shared among Christians, Jews, Muslims, all of them. They have different kind of fasting. And recently, they start a lot of research showing that fasting in different religions, they have really important benefit to the health. So it doesn't matter if you fast in a Christian way, in Jewish way, all of them, they prove to be really beneficial to the health. And this is from Johns Hopkins Hospital, and they have a lot of research about that. And the nice thing, after they fast, they celebrate. They have a huge celebration. For Muslim at the end of the 30 days. For Jews, they celebrate in the night. For Christian, they have different kind of celebrations. All right. So we still continue with the book, with the extremely nice book. This is really international book. This is a global language. So you will see like different students from different universities studying the exact same book. So you can really speak the same language with them, especially if you're studying computer science. And as a reminder, we're still in chapter 2. Hopefully you start checking the book itself, the material. And as I said, we have everything publicly available online for free. You don't have to purchase the book. You don't have to purchase any of those materials, especially the answer to the exercise in the book. We are still in the logic. We will spend really vast majority of the course in the logic layer of the compute stack. And by the end of the course, we are going to jump briefly into the instruction set architecture and the microarchitecture, which is something related to the microprocessor or to the CPU itself. All right. So this is the last topic we covered last time, which is the theorems for several variables. And we stopped at the T10 last time. Hopefully all of that makes sense. We went through the proof, how we could prove that those are correct, except this guy was a bit confusing or a bit new to us, how you could distribute a variable with a plus sign to the things inside the parentheses. This is something unusual. We don't do it in algebra, right? This makes sense when you have b multiplied by c plus d, so you could distribute this over c and d. So you could have it like b times c plus b times d, right? This makes perfect sense to us. However, do you remember duality? What does it mean, duality? Yes, please. Excellent. So we replace the dot with a plus and the 0 with 1 and 1 with 0, okay? So if we do so for this, so the duality of this guy would be b plus c and d. And we said last time we could distribute still the b to c and d, and we could get this form. This is an extremely important. We will see it. We are going to use it in at least 2 examples for today, how we are going to simplify Boolean algebra equation using this theorem, okay? It's a bit confusing, again, but you need to practice it. You could remember it if you want. You could memorize it. For this one, it was trivial. We stopped last time at T11, and hopefully you still remember what it's about. So first, we need to have 3 variables, okay? That's one. Second, one of the variable, we should have it, and we should have the complement of it, okay? Regardless what this variable is. So we could switch the variables all the time. So in this example, for example, let's use the exact same variable. So we have b, c, d. So let's choose b and want the b complement, okay? Right? So in this theorem, we should have 3 variables. So now the other 2 variables, we distribute them over here. So we have one of them here, one of them there, okay? And then we have the other 2 variable as well as another term, okay? So this is the input or this is what we are going to process for the theorem. Now, what the theorem is telling you is that once you see the exact same pattern, for example, one of the variable and its complement exists, and the other two variables distributed over here, this one, you don't need it. Okay, this is what the theorem is telling you. So whenever you saw something similar to this, you could get rid of that guy. Why we do that? Let's see it together. So now we have similar pattern. So you can see we have A, B, C. So do we have three variables? Yes. Now, do we have one of the variables and its complement? Yes. Do we have the other two variables distributed? Yes. Do we have the third term with the two other variables? Yes. Okay, then it looks like we have the pattern. So we could apply the theorem directly. So which one we can get rid of? The third term. So B and C, we don't need it. So we could have this. Now last time we discussed how we could verify the correctness of any of those theorems. We have two ways. What is the first? Yes, please. Excellent. The truth table, right? We could just assume any values to those. How many input variables we have? 3. Excellent. So you could build a truth table with 3 variables. How many output? 1, which is the whole equation, right? And you could build the whole thing and you see whether it makes sense once you compare the result for the whole equation versus having only those 2 terms, right? Excellent. That's the first way. What is the second way? What's the second way to prove these theorems? The second way is to use the other theorems and try to simplify this equation further until we coming up to the same conclusion. Okay? Assuming that, for example, this is, we call it T11, right? So there is other 10 theorems, right? And assume we already proved all of them. So we guarantee that T1 to T10 are correct. Now we could use any of them, all of them, many of them, doesn't matter, to try to prove T11 is correct. Okay? And we'll see this in this example. We're not going to use truth table now. We're going to use the theorem that we studied. So the first thing we said, we want to cancel this one. So before we cancel it, we want to distribute it back to these terms. Okay? So what is missing from here to make it compatible with the other terms? So we have B, we have C, but we don't have the A's, right? Now let's add A's to the third term. Now we cannot just simply say, let's write it here. So here, what is the complement of A? So we have A complement. What is the other term? B and C. So we have B distributed here, C, and then B, C over here. We have plus sign over here. Now, I want to add A's to this term in order to compare it with this guy and try to make consensus out of it. We cannot simply just say A because this is now a new equation. We cannot say A bar because, again, it's a new equation. So likewise, if you remember in Boolean equation, for example, if you have x, y equal z, x, then how you would cancel the x's at the right side and left side? In algebra equation, this is not Boolean. You would simply either multiply by 1 over x, right? Or simply divide over x. So if you divide this over x, divide this over x, then this is canceled out, done, right? Likewise in here, we cannot just simply add the a's. We need to multiply by a value that doesn't change the equation, which is 1. We are going to multiply by 1. And if we do so, do you think anything changed in the equation? So remember, this is multiplication, not a plus. If it is a plus, then it's a big problem. Because if we add 1, then it's always canceling out this term. Because it doesn't matter what value we will have over here. If this is 1, 1 always dominate in addition, and then this would result always in 1. So it's like we are canceling out this term, which is bad. So what we are going to have, multiply by 1, and now 1, we could replace it based on theorem 1, which is anything added to its complement is equal 1, right? So we could replace the 1 with this term, and we are not changing any value. We are not changing any value. Okay? Do you agree on this? All right. So we're going to replace this. Hopefully you understand why we did this process. No need for this. Now, because this term, we're going to cancel it out, we were trying to build a consensus with the other terms in order to simplify the equation. So we said, what is missing over here? We miss the A's, right? Because here we have C, we have B, but we don't have the A's from here. So we are trying to add the A's, but there is no way to just simply add A. Otherwise, to be totally new equation. So we said, let's multiply by 1. And then we substitute by the 1 over this term based on the previous theorem we have in the table. Okay. Now, A plus its complement is always going to result in 1. If you don't believe it, just try with the truth table. Go with A0 and try it out. Go with A1 and try it out. Okay. Now this one we just go over it. I think it's T9 or so, right? Do you remember when we multiply over some terms in parentheses, we could distribute this over here and distribute this over there. And this would result with AB plus A bar C plus BCA plus BCA bar. All right. Now how we could further simplify this. Apparently, we make some consensus between this, for example, and this one, right? We have AB, we have AB. What else? We have A bar C, we have A bar C. Then we are almost there, right? So we could take this together and use different color. Could take this guy. We could take this guy all together. We could take this guy and this guy all together. Now remember, in one of the theories, we said BCA is exactly the same as ABC, is exactly the same as CBA, is exactly the same as CAB. Doesn't matter, right? Swapping the variables in any of the terms, still maintaining the exact same meaning, same equation, and so on. So now you could play with those if you want to make A first, then B, then C. So you could switch this one to A, B, C, and it would remain the exact same meaning. Likewise with this, you could a bit arrange it, A bar, B, C. We're just swapping. We're not changing values. We're not switching the bars. We're not changing the dot into plus and all these things, okay? We're just rearranging the term itself. And now, by doing so, you could now take the consensus. Consensus means whatever shared between the terms, okay? So what is common between this guy and this guy, which is A, B? So we could take A, B. Now, from the first one, nothing left except 1, right? Plus, don't forget the 1. The 1 is extremely important. If you lose it, then if you multiply back, you will not get the same thing. Now, the third term, you take AB as consensus, and you left out with C. Now, the second term, you could take A bar C. Again, you have 1. And the fourth one, what is left? The fourth term, B. Yes, excellent. So we have B. Okay. Any question on this? You're still sleeping? Yes, please. With this one, we're trying to take consensus. Once you take the consensus, once you take what is shared between two terms, then you could easily simplify further. Okay? So there is no rule where to take those consensus. You could take between the second and third. You could take between the first and fourth. You could take between the first and second, and so on. Now, what makes sense is to have something similar to this form. It makes sense always when you take the consensus, you want between the parentheses to have either something and its complement, okay, or something plus 1, or something 1 plus something. Now, this something could be one variable, it could be two, it could be three, it could be four variables. Same story. Okay, it doesn't matter. We would like to look for something like that. Once we take consensus out of it, we left out with this pattern or this shape between the parentheses. Why we are looking for this? Because based on our theorem, we know that this could be simplified into 1. So we could cancel it out. This one could be simplified into anything added to 1 is 1, right? If this is 1, we don't have 2 in Boolean. So 1 plus 1 is 1. If this is 0, 0 plus 1 is still 1. So it doesn't matter what is the input. It's always resulting in 1. Now, we could have the same thing with multiplication. For example, when I have A multiply with A bar, this would result in 0, right? Because directly substitute. If you forgot or you don't feel good to think, just substitute. Replace A with 1. Now, 1 times 0, 0. Now, let's replace A with 0. 0 times 1, 0. So all the time is 0, right? So we are looking for this term, or we want to have something like 0 times A, for example, or 0 times A bar. Okay? Or it could be 1 over here, because you could also further simplify that. Okay? So that's the goal by taking consensus. So always try to take consensus that makes sense, that would result in having something similar to this pattern. And this is what we did. Bless you. So we have this term. We're trying to look, what is shared? Can we take consensus from this and this? Nothing shared. So here is A, here is A bar. So we cannot do anything. This is B, this is C, so totally different. Now, can we take this and this? Yes, it looks like we have AB shared, AB shared. We left out with C. Can we take this and the last one? We could. We have B, for example. So you could take B and you left out with A plus A bar C, which also we have a theorem for it, by the way. So you could take it. That's another solution. So by taking this term and the last term, do you remember we have a theorem said, so if you take B as a common or consensus, then what is left over here? We have A plus, so we are taking B common, then we have A bar C. How we could simplify this, do you remember? We do have a separate theorem for this guy. When you have a variable plus the complement of the same variable multiplied by something else, this would result in one, zero, A complement. If you're always in confusion, just try out. So we have A and A bar, so it's easy to take A. A if it is 1, then 1 plus anything times 0 is 0, so it's 1. If A is 0, then 0 plus C is C, right? So 1 or C. Then then it would result in something with C and A, right? Which is, come on, check the theorem. You have a table. We're going to use it in the next few slides as well. So please pay attention to it. Okay. All right. So hopefully at this step is clear. Now, we reached a point where we could cancel this out because 1 plus anything is always 1. So we could cancel this safely, 1, 1. And then we could have only AB plus A bar C, right? And this is what the theorem is saying. You could, where's the original equation? This guy. You could cancel the term that has the other two variables, and you keep only the first two terms. Did we arrive to the same thing? Yes. AB plus A bar C. Okay. Did you find it out? Not yet? Sorry? Why? They're not there? Yeah, I asked the TA. His name here. Okay. He arrived yesterday late from the conference. So hopefully today he will send them out. Okay. All right. So this is the full proof, how we could prove it using the second method, which is no truth table. Okay. So just by using the existing theorem, how we could extract it, but it's exact same thing as we go over here. Remember, when you take consensus, try to make it more sense such that we arrive to any of those patterns so that we could simplify it. But remember, when we say something like this, it doesn't necessarily mean one variable. It could be really many variables. So this could be ABC, for example, added to 1, still the same thing. You could cancel the same thing, the whole thing into 1. Okay. All right. Do you have any question on this? Yes, please. You mean when we took the consensus for 1? This one? Oh, yeah. So the theorem is saying that you should have 3 variables first. Second thing, 2 of the terms, you should have one of the variable, and the other term should have the complement of that variable. Okay. Now, it doesn't matter which is A, which is B. You could switch the variable, right? It could be something like C bar, C plus C bar, right? And then you need another 2 variables, for example, X and Y. So you distribute them over here. And then the third term would be X and Y, right? You could have something like that. Now, the theorem is saying you could keep these 2 terms. You could cancel this, right? Now, in the proof, we know that this will be canceled out. And we want to distribute this term over the other terms, okay? So we want to make consensus out of this guy. Now, what is missing from this guy compared to other terms? C, okay? We want to add C somewhere, somehow. We want to add it to here, but we cannot do that. We cannot just simply multiply by C. That will change the equation. But we could multiply by 1. And this is not going to change the equation, right? Because we multiply the 1 over this term, which is the same thing. Now, the 1, we could replace it with whatever we want to add. So we want to add C. So we could replace the 1 with C plus C bar. And that's still maintaining the exact same form of the equation. We're not changing anything, right? Now, we could safely distribute this to this, this to that. And then we could take consensus, simplify further, and we arrive to the same conclusion that we can keep those, cancel out those. Good? Yeah, please remember the pattern, because you cannot like intuitively just say I want to replace or cancel out the third term, whatever the pattern is. You have really make sure that you have such pattern with 3 variables. You have one of them as A, one of them the complement of A, and then you could move ahead and simplify it further. All right, the last theorem for today is what we call as De Morgan. So he's a British mathematician who invented this, okay? And it says simply that the nut could be distributed over the variables, but you need to flip the sign. As simple as that. What does that mean? Can you see over here? Okay. So if you have like A, B, C, and all of them going to nut, and this is, if you want to implement it, this is basically a huge AND. You have output, you have 3 input. What are the input? A, B, C, right? And then you just add a bubble to the output, right? This is the implementation of this. What De Morgan said, that you could distribute the nut over the variables, right? But you need to flip those signs. What is the sign over here? Dot or multiplication, and then you just switch it to A. So you could say something A bar plus B bar plus C bar. As simple as that, right? Now, why this is helpful? Sometimes when you simplify, you would need to isolate those terms, okay? So you would break down this huge guy into this. And now if you have in your equation something like plus A over here, then now you isolated the variables and you still have that plus A in your equation. Now you could cancel out some of those. We have A and A bar, okay? You got the point? Sometimes you would need really to break down a huge term into smaller terms in order to work something with the equation. For example, if you have another shape like it could be AB plus ABC whole bar. You could have also here a bar. You could also have another bar over here. And this is common to see it in Boolean equation. How you could simplify this further? First, you cannot play with something that has a nut in it because it's going to change the meaning. So what you are going to do first to cancel this huge nut, okay? How you would cancel the nut over here? You could use the exact same theorem. What it says that you could distribute the whole nut over there, the huge nut gate, into those. You can consider this as one variable and this as another variable. But when you want to do so, remember, you need to flip the sign over there. So this would result in this huge nut. Hopefully you can see it. I'm not sure if it's hidden with this. You can see it? Okay. So now we want to distribute this nut over here and over there. So it would result in A, B. You have a nut initially, this one, and you distribute this one as well. So you add another NOT gate. And now you want to flip this sign. The plus would be multiplication or dot. And then you would distribute it over here as well. A, B, C. You have initially the NOT. And now you are distributing the huge one. So you have it over here. Yes, please. No, no, not at all. So if you have this double, they will cancel them out. We have a theorem for that, right? Maybe not theorem, maybe axiom. It's trivial case. A variable with double not, so not of not, is canceling them out, right? Doesn't make sense, so you could cancel this. But you cannot cancel before you divide this huge one. You cannot say, oh, I have one here and one there, let's cancel them. Okay? Don't do that. if the NOT is this with the whole thing, you can think about it as this between parentheses, and there is this NOT with the whole thing. You cannot just cancel it with a smaller NOT. Okay, that's why we need to divide it over the input. So we can consider this as one input. This is another input. And then this NOT will be divided over the two inputs, like this way. And then now you could cancel them out. Just cancel this, cancel that. Okay? Yes. Yes, please.
Further simplifying that, I mean, if we're I think it's
all right. Okay, so now we took a NOT with a multiplication, but it's exactly the same thing if we have A plus B plus C all NOT. How we could simplify this? We could break down the NOT into all inputs, but remember to flip the sign. So that would result in A bar dot B bar dot C bar. Excellent. And remember the dot, you could show it, or you could get rid of, because by default it's a dot. Okay, so you could write it something like this: A bar, C bar. Okay. Now this is more common in the questions. We don't ask for trivial things like that, but normally we ask something like this. You have whole terms, and the NOT is applied to all these terms. How you break down the NOT over multiple terms. Each term has multiple variables. Okay, so this is more common, and it's easy. You just need to rethink where are the input for this NOT gate. This big NOT gate, where are the input? You cannot have all of those as input, right? Because this one is under NOT, a different NOT gate. So if you want to implement this as a circuit, what you would do, you would take the smaller one first. This is a multiplication, right? So it's AND gate. You have A, B, C. There is a NOT, so there is a bubble. Okay. Now this one is an AND again. So you have, let's erase. So you have another AND. How many input do we have? A and B. But there is a NOT at the top. So there is a bubble. And now all of them, we have OR. So you have OR gate. You remember how we draw it? Then we take this as input. Now with the OR gate, there is a huge bubble over there. So we add a bubble over there, and that would be your output. Now this bubble, it's like we need to cancel it out, but we add a bubble over here, a bubble over there, and switch this into AND. So it would be something like this. Now let's remove it. It will be AND instead of OR. The bubble was there. Now it will be here because we distributed over the input. And this is what we did over here when we distribute this a huge NOT over the input. Now this guy is exactly the same of what we have. Now we have a bubble and bubble. They cancel out because they are on the same wire. So there is a NOT and a NOT on the same wire. So we cancel them. So we replace them by simple wire. And then you have 3 AND gates. Normally, we don't ask you a direct question like that. Normally, we said, you have this circuit, which was given to you. And we ask you, can you implement this circuit using only 3 AND gates? You are given only 3 AND gates, and we ask you to implement this circuit. Okay. Now the question is more challenging, a bit more difficult. You have OR, but if you understand the essence of De Morgan theorem, is like whenever we have OR gate and there is a NOT, then we directly replace the OR with and we switch the bubble from the output to the input or from the input to the output. Okay. So if you need to replace the OR with and or the and with OR, you directly go with the De Morgan theorem. Okay. Now you could come up with this bar over there yourself. It might not be given to you. For example, you might be given this equation, and we ask you to get rid of this plus sign over there. Likewise, when we added the 1, do you remember what we did over here? We multiplied by 1 because we want to add a, but we couldn't add a separately. So 1 multiplied by 1 and then replace the 1 with this. So over here, we want to replace this, but we cannot simply say just get rid of the plus sign and add a multiplication. So to use De Morgan, what we should do, we need a NOT. We don't have a NOT over here, so we could add our own NOT. But if we add a NOT over there, we are changing the equation. But if we add double NOTs, we are not changing the equation. Now the exact same meaning is already maintained, right? Because a NOT with NOT, they will cancel them out, and then we get back our equation. Yes, please. This one? So we have A and B. We have A, B, and C. So we implemented this first. I don't know why we did that, but we implement this first and this second. But it's same thing. You could implement this first, which is this circuit, right? So you could draw it first at the top and then move ahead with this term. So you could implement this in second, doesn't matter. Okay. And now we have a plus sign in the middle, which means addition or. So we add the OR gate over there. And then we have a huge NOT at the top. So we just add it over there to the out. Good? Right? Now, if we want to apply De Morgan, we have the NOT at the output. We need to distribute it over the inputs. So we add bubble, right? And then switch this into AND. The plus sign is OR. To replace the OR, we replace it with AND, which is multiplication. Okay? Now, when we have bubbles at the input, and we have bubbles over there, so they cancel each other. Back to our story over here. If we have two NOTs, then they cancel each other, but we don't want to cancel them because we add them, right? So we add these two. Now, how we could get benefits of De Morgan? We consider the one inside over here. We want to distribute only that one to the input. So remember, this one input, this another input. And there is a plus sign because our focus is the plus sign. Everything to the right side is one input, to the left side is another input. This way, you could really simplify the way you are looking at the equation. Now, we want to cancel this out. So De Morgan's saying, just take one of the input, do a NOT to that input. The plus sign would be dot. The D would be with a NOT. And remember, there is the outside one, so we just added. So we went from this We went from this guy to this guy. Now we could go further. This one can be also distributed over these three terms. But remember, there's a dot here, a dot there, then switch it into plus sign. Okay, so it's like A bar. We are distributing this not over these three inputs. There's a plus, B bar, plus C bar. There's a dot, and then D bar, then all with a not. Okay. And you could go further. Now, if you want to focus on the dot, for example, so you consider everything here in one side, everything here in the other side, and then distribute this huge not over the input. So you distribute this over this entire thing over here and over there, but remember this to be switched with a plus sign. Okay. Now you'll see it clear when we have real question about real equation and how we want to simplify using De Morgan. But remember, De Morgan is applied to the and the or. So over here, we apply it to the and. So whenever we have AND gate, we just distribute this whole not over the variables, and we have the plus signs. Or the duality, just replace the dot with a plus. We don't have 0 and 1s over here. So we could have this form out of that. And we could do this exact same thing. We distribute the whole not over the variables, and we switch the plus sign with the dots. Okay? Any question? Any question? All right. So this is, we already went through it last time, if you remember, how to prove any of those theorems. The first one, we call it perfect induction. Why we call it perfect? Because we go through all possible inputs. When we build the hash table, the truth table, this one, when we build the truth table, we are taking all possible options. If this is 0, if this is 1, if this is 0, if this is 1, and so on. Okay, that's why we call it perfect induction. And then we could fill this with the values, and we'll see if this really equal the exact same thing over there. Right? This is the first method. The second method is just to use other theorems. For example, we are using here theorem 8, theorem 3, 2, 8, and so on, until we arrive to the same conclusion of things. Okay? We already covered this last time. Any questions so far? Yes, please.
Sorry, I'm not. You said we applied Morgan to the case. We put the bubble on. So if we have even inputs, probably apply the bubble to both.
No, you should distribute it over both. Where's this guy? Yeah, I don't want to use this. Okay. Probably we shouldn't jump into 3 variables. Let's stick with 2 variables to make it clear. So give me something. So we'll go with 2 variables. Do you want plus or multiplication? Okay, so let's go A dot B. Okay, and we should have a not applied to both of them. Okay. Now De Morgan said, if you wanted to get rid of this huge not, you could distribute it over the input. Over the input. Remember, input of what? We distribute it over input of what? Input of this gate, whatever this gate is. Now, if you find it difficult to imagine it, just implement it using gate. What is this? This is AND, right? AND gate. And we have 2 inputs only, 2 variables, A and B. Now, the output of this has a bubble because there's a not, right? So we just add a bubble over there. And if this is Y, for example, then this is Y. Okay? Yes, if there are another not over here, then it means there is two bubbles. If it is addition, same thing, A plus B, there is a not over there. Then this is OR, right? So OR, we implement it this way. So this is OR, right? But there is a not at the whole thing. It means the output is inverted. The output is inverted. So we need just to add a bubble over there. No, this for the whole thing. So you can think about it as there is a parenthesis over there, and then the not is applied. It means calculate this first, and then do not. So you could think about it as, or you calculate A and B, and that would give you the parenthesis, right? So you're done with the parenthesis. Now you have a not at the top. So which is another not gate. They have or and then not gate. A not gate is a bubble at the output. So this is exactly the same thing as this. This is a not gate, right? Triangle with a bubble at the end. Do you still remember the logic gates? Sorry, we had this lecture online when the storm was happening here. Yes, please. Okay, excellent point. I'm not sure if this side is better than the over there. Should I use it? Okay, let's see if the bar is not at the top, it's already distributed. For example, you want a multiplication or plus. Okay. So A plus B, but you have bars over here. This is what you said, right? Okay. Now, the operation here is OR, right? So we have OR gate. And this is the output. Now it's a bit tricky. What is the input to the OR? Excellent. Is A bar and not A, and B bar and not B, right? So the input is A bar, not A. So we cannot write A and B. So we should invert each of them first separately, and then we feed it into the OR gate. That means we should have a NOT gate here, triangle and then a bubble, triangle and then a bubble. And here is A and B. Right? So now we flip the inputs, and then we feed them into the OR gate. So this would be that. But simplify it. We don't need really the nuts over here. We could just say there is a bubble at the input over here. And it's exactly the same thing. Yes, please, go ahead. No, the buffer doing nothing. Buffer, just when you transmit a signal into a far distance, you might lose the voltage. So we want to reconstruct it. We want to build it. Yes, exactly. If there's a noise, for example, coming into the input, the buffer will cancel out the noise and reconstruct a perfect signal. So if the input is 1, the output always 1. If the input 0, always 0. It does not change value, but it's improving the voltage. And we use it normally to transmit a signal from one point to another point. We're going to have some resistance impeding the voltage. And then that voltage is adding up noise, right, over time, over heat, over distance, the same topic we discussed. And then we need to reconstruct, rebuild that signal. Okay? So buffer in this perfect scenario is doing nothing, basically. So we use it in real life when there are noise or resistance and so on. Okay? All good? All right, we have 4 minutes before we move to the assignment. Maybe we shouldn't jump into the other topic. But do we have any questions so far? So we'll see De Morgan a theorem a lot in the example. I was preparing a lot of examples for you, but it's okay. We can skip until next lecture. I don't want to rush it. Did you digest this topic? Likewise, you could go back from this form into a not on the whole thing. How we could have a not at the output rather than at the input over here. De Morgan, excellent. So we could cancel out these. Let's use another color. We could cancel out the bubbles at the input and place it at the output. And then we need to switch this guy. This is OR. We need to replace it with NAND, which will be this one, A, B. Now we place this plus with the dot, and then we have a not in the whole thing. So this is really equivalent to this. Okay? And likewise, this is equivalent to that. Do you agree all? Do you all agree on this? Likewise, if this is a plus, then this is dot. Okay? And again, doesn't matter if it is 1 variable, 2 variable, 3 variable, doesn't matter. You can consider anything to the right side of the plus sign as 1 variable. So when you have a not, you distribute it over the whole thing. And then the other side as another input. All right? Yeah, sorry, I know you participated a lot. But we are going to give the nots for whoever finished the quiz first. Okay? How many of you missed the first assignment? 1, 2. We have 4, I think. 4 students missed it. The first assignment, the first in-class assignment. How many of you missed it? All right, let's see. I'm going to skip all of this. Please close everything. I prepared extremely easy assignment. It's only 1 question for those who took the first assignment, and 3 questions for those who missed the first assignment. Okay? So we are going to only have 1 question, which is extremely easy. So far, we got only 1 in-class assignment, right? Which is this paper, right? Whoever took that, now the second assignment will be only a single question for them. Whoever missed it, they have to take 3 questions now. Okay? Yes, please. Why? Why? You can try. We will see. No problems. No problems. You may get lower grade. The first one is only easy. The second and third questions are not really easy. But you can try your luck. Okay? Ready? We have about 15 minutes. Okay? So I think it's good enough for the first question. Ready? Please remember, close everything. I don't want to see books, laptops, pad, any screen. Okay? Please don't look at your neighbors. Right? Ready?